next problem is called subtree of another tree. We are given two roots of two binary trees, root and subroot. We have to return true if there is a subtree of root with the same structure and node values of subtree, and false otherwise. So basically we will have to check if the subroot is contained in the first tree marked by our root. A subtree of a binary tree is tree that consists of node and tree and all of its node descendants. So basically this node and the descendants. The tree could also be considered a subtree of itself. So if we have the same two identical trees, basically then the subroot is the same as root, but it's also its subtree because we can consider a tree a subtree of itself. So in this case, we have 4 here and 1 and 2. So basically all the root and all of its descendants are contained in the root. So we just return true. Now for this case, we have 4, 1, 1 and 2. And here we have 4, 1, and 2, but we also have this left node, so it's not completely identical. So we just have to return false. Now to solve the problem, we basically have to check if the current root can be a good starting point for us to check if it matches the subroot, the current subroot, and all of its descendant. If it doesn't match, we would try to search it in the left subtree and the right subtree, which calls for recursion, basically. So there are 3 cases. Either the root is a good candidate, and we will return true, or we will find that that subtree is that the subroot is a subtree of a node in the left subtree of the root, or in the right subtree of the root. And how do we actually check if they are a good start, if they are the node that matches the beginning of the subroot? Well, basically, we already implemented the same tree functionality in the last problem. So we would just call the same tree on all of the nodes from the root from the first tree, and check if that's a good starting position to match the structure and values of the subroot. If it is, we just return true. So we'll start by checking if the root and subroot, either one of them is null, and if they are, we have to check if both of them are. So this is our base case, because we will be calling this subtree recursively. And if they are both null, then we will just return true. If not, we will return false. So we will call the isSameTree function on basically the current root and pass the subroot as the second tree, or to check if the current root is a good candidate for starting of the subroot. And in the case it's not, we will have the second and the third condition. So basically checking if we have a node in the left subtree or the right subtree that's a good start for the that's a good start for that's a good match for the subroot. And we will just have basically the same definition implementation of the same tree that we had in the previous problem. Now, because for each node in the main, in the first tree named declared by root, we will check if it's a good match for the subroot. That means that we'll have time complexity of m times n, where n is the total number of nodes in the root tree, and the m is the total number of nodes in the subtree subroot tree. Now for the space complexity, we will, in case we have a skewed root, the first tree, we will have a stack up to these lengths the size of n, where n is the total number of nodes in the larger tree.